Hello everyone. In this video we are going to consider another example of checking the stability of a closed loop system using the Bode diagram and Bode principle. The controller is provided as a proportional one, so GC of S is equal to K, where we are going to consider two values for K, 3.165 and 10. And the plant itself is given as 1 over 1 plus S to the power of 3. So it has 3 poles at minus 1. We need to draw the asymptotic Bode diagram and then compute phase margin from the drawing. We'll take omega c as its approximated value in the asymptotic diagram. And we'll compare the result with Matlab, where we draw the exact Bode diagram. So we will have indeed L of S equal to GC times GP, which will be equal to K over 1 plus S to the power of 3. So L J omega will be equal to K over 1 plus J omega to the power of 3. We have 3 poles at minus 1. Therefore, the Bode plot for this system could be drawn in this way. We have the x-axis for omega. First, we consider K equal to 3.165, which is basically equal to 10 decibel. We will have at omega equal to 1, we'll have the corner frequency for 1 or 1 plus j omega. We'll have 3 terms with 0 dB till that point, and then let's say this is our 10, 100, 10 to the 3. We'll have minus 20 decibel per decade for each term. So we'll have 3 terms like this, and we will have a single term with a value of 10 decibel. This 10 dB stands for K, where K is equal to 3.165. When we have K equal to 10, we will have 20 decibels indeed. So depending on case A or B, here we have K equal to 10 or 20 decibels. In terms of the phase, we expect to have 3 terms where at omega equal to 1 we will have minus pi over 4. And the asymptotic phase will be like this. We would need to have 3 terms like this, and here as well we have 3 terms. Now the overall Bode plot that we will get will be for K equal to 3.165 in terms of the amplitude. We will have approximately this. So till omega equal to 1 we will have 10 decibel. After that we will indeed have minus 60 decibel per decade for the slope, because we have 3 terms with minus 20. So minus 60 means that if we have 10 here, after 1 decade we will have minus 50. So here is minus 20, minus 40, minus 60. Therefore this will be the value after 1 decade, and after another decade it will become minus 110. So it will indeed continue like this, minus 60 decibel per decade. This is what we get for K equal to 3.165. If you have k equal to 10 or 20 dB, then the amplitude plot will move 10 decibels upwards. We'll have 20 here. At this point, we'll have 40. And then in terms of the slope, it will be the same, minus 60 dB per decade. In terms of the phase, both of them will be the same. We need to introduce 3 components like the one that we have here. At omega equal to 1, we will have minus 3 pi over 4. So we'll be here. At omega equal to 10, we will have minus 3 pi over 2. Let me extend the axis. So we have minus pi over 2, minus pi, minus 3 pi over 2. At omega equal to 10, we will have minus 3 pi over 2, and asymptotic phase plot will be like this. Now, if I want to find out the phase margin, we would need to determine the omega c, the corner frequency. For k equal to 3.165, the corner frequency will be around this point. We can indeed find the exact value. You know that it will be the corner frequency if we have amplitude of L equal to 1 or 0 dB. So we can find it. We know that for this case, the amplitude will be equal to amplitude of L of j omega will be equal to k, which is 3.165 times 1 over square root of 1 plus omega squared to the power of 3. So through this we can find the exact value equal to 1. We can find the exact value for omega. It will be somewhere between 1 and 10. We can check it from Matlab as well. But once we found it, we will come back to the same indeed frequency, and this will give us the phase margin. So this value here will be our phase margin, and we can see that it will be a little bit less than 45 degrees, but still it seems that it would be a positive value. We will see how to find the exact value using Matlab. If you want to calculate it, once we have the omega c here, we would need to find out phase margin as 180 degrees plus phase of L of j omega at omega c. And phase of L of j omega will have 180 degrees minus inverse tangent of omega c over 1. So once we have the value for omega c, the exact value for phase margin will be also obtained. When we make the k equal to 10 or 20 decibel, as you can see here, the omega c, the crossover frequency for gain will increase, and eventually the phase margin will become negative. And once this happens, the closed loop system will become unstable. Now let's see what we get in Matlab. In Matlab, I already have declared the transfer functions as g and g2, as you can see here, with 3.165 and 10 for the gain. And I have drawn the Bode diagrams for them. You can see here how the Bode plots would be. In terms of phase, both of them are the same. In terms of amplitude, the one in blue is for the first case where k is equal to 3.165, and the black one is when we have k equal to 10. We can right click on it and check all the stability criterions. The blue one, which is for k equal to 3.165, tells us that the phase margin is equal to 38, and the frequency is almost at 1. So omega is equal to 1.08 and phase margin is 38 degrees. For the second case, the crossover frequency is equal to 1.91 and the phase margin is negative -7 degrees. So the closed loop system will become unstable. In terms of the gain margin, let me explain you how you can find it first. In terms of the gain margin, we would need to first determine at which frequency the phase becomes equal to -180 degrees. This will give us the phase crossover frequency, omega CP we can call it. And then we move to the amplitude plot. We move to the amplitude plot. At the same frequency, we find the difference between the amplitude plot and the 0 dB, and that will give us the gain margin. And you can see here the gain margin for two cases. For the first case, the gain margin is positive. It's equal to 8.6 decibels. And for the second case, which is drawn in black, it's negative -1.94, which means that our closed-loop system will be unstable. Okay, so we are kind of done with this example. We drew the approximate body plot. We found the exact one. We determined the stability of the system. In the first case, this closed-loop system will be stable. In the second case, it will be unstable. And we plotted the body diagram using Matlab and determined the gain margin using the diagram, the body diagram. Alright, so that's all for this video. Thank you for watching and see you in another video later.